Hi, my name is Sabu Francis, and I am at a place called SIBA. SIBA is Center for Incubation and Business Acceleration. It's quite wonderful working here. I'll just show you around. It's a beautiful environment, and it's in the night today on July 2nd, 2019. If anybody wants to join me on this journey on a new kind of architectural practice, a new kind of architectural research oriented practice, please do join me. My email address is sabu at the rate limeandleap.com, limenleap.com, and you can write an email to me, and it'll be nice to get some people to work along with what I'm doing. Actually, I wanted to make this video yesterday, and I did start it, but I couldn't finish it, so I'm making it again. Yesterday was July 1st, 2019, and 28 years back, that is when I was around 28 years, um, I had got the JIIA Special Award for Architectural Research. And that time in my treatise, I had submitted some basic principles of mathematics, and I had included my software, the DOS version those days, in the sleeve of that particular report, and I'd submitted to the Indian Institute of Architects. And I'd said that I can explain this, but I think 28 years is never too late. And now that we have the internet and we have ways by which we can make our own videos, I hope that I can explain this better. Another 28 years have passed by, so I'm now more than 28 years actually. I was 29, almost 30 years when I was got that award. So I'll be reaching 58, though I feel 28 at heart. And without much wastage of time, let me explain what is TAD all about and why is it that as architects we should be bothered. So before I explain TAD and how it works, I cannot explain the whole thing here, but I can give you the core principles. Let me broadly tell you about two kinds of computer-aided drafting and designing which people generally do. One is known as surface modeling, and the other one is known as solid modeling. And there are two distinct types of software, and there's a reason why such software, why are they needed, and in which areas are they useful, and where we should use what. Now, before that, okay, I'm just keeping on going backwards. Why is it that an architect should be bothered about something like that? So, for years, literally from the Renaissance time, we have been using drawings to talk about our designs as an architect. And we think that that's a way to go about explaining what a design is. And we need to really pause and ask ourselves that you mean to say in 700 years, we have no other way to talk about our buildings other than make drawings. In fact, if you were to resurrect some of these Renaissance architects, Brunelleschi or one of those Michelangelo, all these people, if they were to be resurrected and brought here, and we showed them our drawings, they will not get confused because they were the one who invented that kind of drawings. What they will get surprised about is the material we use and the sizes of rooms and the thicknesses of the material. All those would be a little surprising, but the drawing itself, the technicality of the drawing will not be a surprise to them. So in 700 years, are you trying to tell that we never figured out any other way to talk about our design? And when computers came in, what we did is a large part of this software, they just took whatever which were being made as drawings and they just simply put it on the screen and they are still making drawings. And that we are not fully understanding because possibly computers is a very young subject. Okay, so that's a backdrop why we need to know How does this software work? How does computer-aided design work? Actually, there's nothing called computer-aided design. That's my uh, core point, but people debate with me all the time. I call it computer-aided drafting. It's actually making drawings. Maybe they're making 3D drawings, all right, but they're making drawings. And therefore, you really cannot call them computer-aided designing. So that point which I told, there are two kinds of such software. One is known as 3D software, okay? One is known as solid modelers and the other one is known as surface modeler. Now I got my intern who's working for me. She's from IIT Kharagpur only, and her name is Kavana. So she made this models for me. I said that make one cube with some stiff paper and make another one with a hole in the center, hole through it. So I'll use this as a prop to explain what is this all about. So if you take a surface modeler, what it does is that internally it represents, say a cube like this, it represents it by the thin faces of that cube. So it's hollow inside, as you can see. And the problem with this is that it really is not representing the solidity. Suppose this was a wooden block which we have to model. This block obviously needs solidity inside. There has to be some solid material inside. But what we did is we just put this pieces of paper, 6 faces, and we got a cube. Now it's all right to look at it. When you look at it, it looks solid enough, but really speaking, it's not a solid. Now, this is what surface modelers do. What they do is that they don't get into the detail of what that particular solid matter is. And instead, they just use very thin, infinitely thin planes and then kind of attach it together. So visually, it all looks nice. Now, this has got serious limitations. Like, for example, you really cannot talk about any property of this material because the software itself doesn't know what is there inside it because it's not represented it, so it doesn't know what is there inside it. And the other problem is that you can easily edit, as you may have seen in 3D Studio Max and even SketchUp. You can make a cube like this, and then you can just remove one of the faces, and then it'll get empty, and you'll see the thin planes over there, right? And then later on, you may decide to stick it back again, and it visually looks okay, but it may leave some chinks. As you can see here, there is a small chink here. It's not stuck properly. And the same thing happens even in such 3D software, which we don't realize because when we model it, say in SketchUp or whatever, it looks solid enough. It looks as if all the planes are closed. But when you start rendering it, it turns out that particular chink of light may come through this particular slot. And this is actually perplexed a lot of rendering studios and people who work with 3D Max and SketchUp and all that. They carefully constructed a complete building and all that, and then they start rendering it, and they had left a light inside it, and that light starts seeping out from the edges, which is not fully closed, and they wonder why did that happen because it looked close. It looked quite closed. In short, surface modelers are really just simple things. It does not really have any capacity or capability to even understand what is really going on in this material. Solid modelers, on the other hand, are a different kettle of fish, and they have the capability to model the solidity of that particular thing which you're modeling. Say you're designing an engine or you're designing this bottle. Now this bottle happens to contain water here, so it's holding this water inside, but it's not just this water. The thickness of this plastic which is used, the thickness of this cap, the all that is very important when you're designing such a bottle. If you're a mechanical engineer or you're a product designer, you would like to know whether can this cap be crushed by the normal action of a person's hand, and that will determine the structural rigidity of that particular part of this device. So when it's getting modeled in a solid modeler, that solid modeler actually can analyze that they have routines which will try to actually crush it, and you can simulate the crushing of that particular part of that solid, and that can only happen if that material inside that outer surface is also present inside the software. So such software can be very complex, and it can occupy a lot of resources. It will require a lot of space on the disk and in your memory. And that's why these kind of software are can only be run on very high-end computers, and it will require a lot of RAM, and it will be usually be very expensive, because the kind of internal routines which needs to be done to represent this solidity of that particular solid model, all that is pretty complex. Okay, so you have this two broad divisions of way of representing 3D. And there are many people who get confused about this. For example, people think that, oh, you can design in SketchUp, or you can design in 3ds Max. There are people who design in 3ds Max. There are people who design in Rhino. That's also largely a surface modeler. Even AutoCAD that way is largely a surface modeler. They do have an what is known as an ACIS edition for solid modeling, which makes AutoCAD even more heavy than what it already is. And but largely AutoCAD, 3D Studio Max, they're all surface modelers. They will allow you to model things visually, and therefore they are good for rendering. Lumion, they're all good for rendering. And but if you ask them what is the cost of this, what would be the material inside it, that will be very difficult for them to say, because they never put the data didn't go inside. There is nothing inside that particular, say in this cube, there is nothing inside that cube. It's just the surfaces which is there. Now this has been a big confusion, and many of these companies have actually exploited this confusion. Even SketchUp is considered as a way to talk about buildings and design and everything. It's quite a nice software. The UI is very nice, but inside that it is still a surface modeler, and you can easily see that. You can just construct a 3D and just remove one face, and you'll see the edges of all the planes which is there. Obviously these kind of thin planes do not exist in the real world. The real world contains thick planes. Even in this bottle, though you can technically say that the thickness of this plastic for this bottle is very thin, but even that thin is actually quite thick as far as the modeler is concerned. And solid modelers do a good job of modeling things like this. They can guide the designer and say that, if somebody were to press this, it will flex so much, or it will crush. All that analysis can be done. So these are the two situations. Now, as far as architecture is concerned, we were kind of a forgotten lot by these big software companies. Why so? We architects think that the world revolves around us. Probably it does for some architects, but the software companies don't look at us like that. We are just a small lot. When these software companies, even AutoCAD, when they made their software, it was directed at people who make technical drawings. And to the young architects here and those who are just students watching this video, you may be surprised that the number of people who make technical drawings similar to architects, technical drawings are huge. Like all the manufacturing industries will have some drafting section where they are sitting. In the olden days, they will be sitting with their pen and paper and T-squares and all the things which we architects use, and they'll actually make sections and plans and everything. But they're not making sections and plans of buildings. They're making sections and plans of things like bottles and whatever mechanical engineers and civil engineers they do. So there's a whole lot of people who do technical drawings. Naval architects use technical drawings. manufacturing industries, car industry has been a big usage of such drawings. So it's not just architects who use these drawings. Architects are a holy lot, I do agree, but architects are a very small component. And why these big companies did not really look at us is because they get a lot of money when they have to sell software to a big department in some, say, a car manufacturing company. So there nobody really asks questions and say, okay, this costs so much, okay, we'll pay so much. And then they have 50 people who are using that software. And the software company is very happy. So AutoCAD, Autodesk, they all started there. Then they realized that architects are also using this. And that's where we architects thought that that's made for us. Okay, only recently there are attempts. Of course, Sketchup is leaning towards regular architects, and few other software are there which is meant for regular architects. But by and large, the history of the mathematics behind both solid modelers and surface modelers did not originate from architecture. It originated from mathematics. It originated from mechanical engineering. It originated from manufacturing industries issues and things like that. And then it came over to architecture much later. Maybe some architect went over to some car manufacturing company and said, oh, you're using this software to make these drawings. Why can't I use that same software? And must have started something like that. Anyway, why am I telling you that? Because when you talk about solid modelers and surface modelers, people thought that that's the only way to really model this particular 3D around us. But it turns out there is a third way, and that was the paper which I submitted in 1991, July 1st, 1991. I was sitting in a largely empty auditorium at Nehru Center because that day it was a Sunday and there was, I think, Ramayana or something going on TV. So practically nobody attended that function. It was a little bit embarrassing, but it's okay. Nevertheless, that was the pretty nice award to get. It gave a very young architect a good kick to think about all this a lot more deeply. I'm really grateful that a lot of people were there who encouraged me, including DG Parab, Charles Correa. A lot of people were there who did know that, okay, there is some glimmer of hope of doing something in modeling architecture. And this journey has been pretty nice, and I hope I can explain to you why this third way of modeling is probably useful. And the third way is neither a solid modeler nor a surface modeler. And that's the way by which DAD models its buildings. Now, don't shoot me because it doesn't work like AutoCAD, or it doesn't work like SketchUp, or it doesn't work like Revit. But try to understand what is the underlying principles inside this particular software. And I will try to make it easy for you. You take this cube, and there was this very prolific writer and amazing genius. He's considered as one of the brilliant minds for centuries. I think he has written over 800 books. This is somewhere in the 16th century. His name is Euler. His spelling is Euler, but people pronounce his name as Euler. And he came up with a lot of theorems, a lot of very neat explanations. He was a kind of a cherubic guy with, I think, 6 children, and generally happy guy and very prolific and very intelligent. So he came up with this observation. You can think about it with the cube. So a cube has got 6 faces. It's got 8 vertices. So 8 plus 6 is 14. And it's got 12 edges. So if you count all the edges, the straight lines, so it's like one dimension is the vertices, the corners, that is. Okay, that is 8 in number. 2 dimension is, sorry, 0 dimension, I'm sorry, let me correct that. 0 dimension is the vertices, the 1 dimension are the edges, and the 2 dimensions are the faces. If you put them all together, you get a lovely invariance at the end of it. That means if you add the vertices, which is 8, and add the faces, which is 6, so 8 plus 6 is 14, and then you subtract the edges, which is 12, and then you get 14 minus 12, that is 2. Sorry, I don't know why I had to pause. So you get this magical constant at the end of it. Now you may wonder, okay, you subtracted some edges, subtracted some faces, and did something with vertices and all that, and you got a number 2. But what was fascinating is that Euler was able to prove that this kind of stability, at the end of that equation you get 2, you'll get for a whole class of such objects, and these objects are known as convex objects. So if you take a convex object and then you take the faces and do this particular equation, you'll always end up with the number 2. Now why should that be such a big deal, you may ask. The big deal comes when you start making a hole through it. The moment you take that cube and make a hole through that cube, you find that obviously the number of faces has gone up, because there are lots of faces inside this cylinder going through this cube. This is also, by the way, surface model. There is no solidity inside this. This is just a dummy construction. And that's why this became little popular, right? When you make something in 3ds Max, 3D Studio Max, and or in Sketchup and all that, you can actually make a hole like this, and it does look solid enough for you to do your work. But they're all visual characteristics. That's it, nothing else. If you were to model the solidity inside it, suddenly you are in a deep shit, because that material that has to hold all the faces, all the edges, all the vertices, and the moment you start making holes through all this, you have a big explosion of memory to be consumed inside that computers. Imagine this: you have one cube, you have another cube, and all it had was just one hole through this. And suddenly the memory consumption between these and this is drastic. Like this will consume very little memory, because you just have to make 6 faces and edges and vertices. And this has got a whole lot of vertices and edges and faces, because you have to represent those planes inside, which represents that hole also. So the memory goes for a toss. Even in surface modelers, it will actually grow. And in case of solid modelers, it grows even more, because it has to also represent the solidity inside it. What do you do? What happened is there was a big con which is going on, and which has not been explained to architects. As it is, architects are this very exclusive lot, and many architects whom I teach, they think that, a lot of students actually tell me this. I got into architecture because I don't want to do maths. Well, architecture is the foundation of a lot of mathematics. Whether you like it or not, maths is there inside architecture. Geometry is there inside architecture. So you better fall in love with all this. And you don't have to get into formulae and all kinds of complex stuff. You just have to understand things conceptually. And that is the part where these people exploited. They never told us, these software companies, that, you know what, we are just taking something which we were using to design bottles, and maybe something as large as a car or an engine in the car and all that, and they are complex things. Even a bottle is pretty complex. If you have to model this particular cap, it's got that groove over there, that spiral groove, and there's a spiral groove on this particular side also. So all that is pretty complex modeling. So these are not trivial things. But one thing they didn't tell you is that the amount of data which it takes to make a bottle is relatively very less compared to what happens in a building. And that part they didn't tell you this. And what they did is that they took that approach of solid modelers and surface modelers and simply brought it over into architectural software. They said, okay, we'll just ask you to buy a bigger computer. We'll ask you to put more RAM in it, more hard disk. I mean, that's your problem. But I don't want to write another software just for architects. As it is, architects is just a small bunch in the whole, sphere of their business. So why should I now talk about another software and build it up from scratch? So we got conned in that. I strongly believe that we got conned, and we need to really ask ourselves, is this the way we go about modeling a building? A building is the largest hard disk you can ever get. And this is something you need to reflect on, right? You look at this room. I just showed you the room here. This is a pretty large room, but even if you go for a small room, there's a lot of memories there. There's lots of treasured conversation which has happened. You go to a room somewhere, say you were in a college, and you had such lovely friends over there. You go back to that college canteen, and then you actually recollect all those, some of those conversation at least. So in one sense, that architecture has locked in those memories there and kept it for you. So architecture is not just the thing about the material which is there, and we need to discuss that and the geometry of it, but there's a lot of non-visual properties. You have to talk about the cost of that material, who's the person who made that table, who's the one who nailed that shelf into the wall. These are all actually important things in some situations. So unlike that car engine or whatever the solid modelers and surface modelers modeled, which is to be used in a manufactured situation, you take one car engine or you take one bottle, you design one bottle, it's going to be the same bottle 10 million times, because they make that injection molding machine, and then it will mold out these particular bottles one after another, and it's the same thing again. But that's not how architecture is. Every piece of architecture is going to be different, and each building will have its own set of properties. And beyond that, that architecture is like a sponge. It is absorbing memories, absorbing conversation. It is letting people coming in and going out. There's going to be a lot of such what you say, analysis of this at some point in time. And we don't do all that, right? We don't design a building, and let's say, for example, I've designed a building and I want to analyze it for the possibility of a fire in that building. What do? You got a 30-story building, and if you want to simulate, and all this is possible, okay, it's possible today, provided the data was constructed like that, that you make a building and then you want to think that what would happen in that building if there are so many people inside that building. What would happen if there's a fire or an earthquake? What happens to the people? You must have seen videos of building shaking and people modeling earthquakes, on effect of earthquakes on buildings. But what about simulating the people themselves inside? These kind of things are not possible, because we are saddled with a very bad way of talking about architecture, which is consuming itself a lot of memory. Okay, so what is the TAD way of doing this? And that is pretty interesting actually. It's very simple if you were to look at it. What I realized when I understood all this kind of 3D geometry, and how 3D could be represented, and how the moment you start representing holes, it started becoming very large. The data started becoming very large. So that then I started thinking that, there is one material which architects always handle, but it is not material as such. It is what we call a space, and space is one particular kind of volume in which there can never be a hole. You cannot put a hole into a hole, kind of thing. You cannot take space and puncture a hole through the space. That's not going to happen. So if I were to model everything as volumes of spaces, instead of talking about material, then I can make that modeling very, very efficient in terms of how much work can be done with minimum amount of resources. Now, how do you do that? So I was very fortunate to discover that in architecture, you can just assemble three kinds of volumes of spaces. Okay, one I call this as an envelope. Okay, let's see. A quiz question. Has anybody seen what is there inside this? What was holding this? Okay, this is an iPhone case. This is not my iPhone. I found it here. Somebody else was using an iPhone. I think he bought an iPhone and the case is lying here. So this is, this volume here is what held up that particular iPhone, right? What if we were to look at this volume as the most important thing which we need to now think about, which is what we do, right? We are not termites. We don't live inside the wall. We live away from the walls. We live, what do you say, enveloped by these walls. So I started thinking, what if I were to look at architecture as like Russian dolls? Let's take this entire volume here, okay, and I say that is an envelope. Think of it like a shopping bag. Think of the spaces within that particular shopping bag, and that would be the what I call as atoms. I use the word atoms because atom is something which you don't further subdivide. Now, what exactly is an atom? The architect can decide whether it's one part of the room or the room itself. All that is up to the architect. The outer silhouette of the building is the envelope, and there is a third thing which is the connector, which connects the outer volume, that the outer silhouette, which is the envelope, to the inner atoms, and those are windows and doors and things like that in case of a regular building. But if it turns out that, sorry, I'm mixing up my words, it actually turns out that you will see atoms envelope connectors at every scale of examination of a building. You take a table, you will see an outer envelope, you will see the atoms where you put your knee inside that, and you will see connectors if there's a hole to get the the wires out through the door, through the table, out from the lower half of the table, and you bring the wires up, so that could be a connector. So if you really look at it, you can actually talk about all of architecture as a set of volumes, okay, which don't have holes. The volumes themselves don't have holes because they're all spaces. And how do you get the built matter? So when you create the outer envelope, and then you create the inner atom inside it. Let me take this cover here. Okay, think that this particular thickness is larger than this. I don't have such a model. I was trying to make one, but then rather Kavana was trying to make one, but it's not yet ready. So if this was thick, what would have happened? There would have been a smaller atom here, and this is the outer envelope, which is the silhouette of this particular. Now, in this case, this is just one room here. You could do this with multiple rooms. So each room is an atom by itself, and then you envelop the whole thing with an envelope, and then you bring in the connectors. Now each of those volumes don't have holes. That's the beauty of TAD. So it's neither a solid modeler nor is it a surface modeler, but it is something which talks both about spaces as well as the built matter. There's a lot of research about this. I've submitted 7 papers internationally. My last paper was on the linguistic aspects of this. Why should we talk about our buildings as if it's got atoms, envelopes, and connectors? We are not physicists, somebody may say, and say that, we are not talking about atoms and electrons and protons and neutrons or whatever. I just happened to use the word atom simply because it meant a space which is not further cut up or divided. That's it, nothing much more than that. So now what happens is that we are now talking about a way of looking at buildings which is very easy on the resources. That's why if you were to use TAD, you'll find that I can talk about very large buildings literally in kilobytes. Literally in kilobytes. You see the way TAD works, you'll be surprised at the kind of modeling it can do with just such small amount of data. So that's what my entire introduction of what TAD is. It's got some fair amount of maths in it. It talks about fractals because these are all self-similar structures. So you'll see atoms, envelopes, connectors everywhere. All that, I don't want to confuse you. If I were to summarize this, what I was trying to tell you is that we have been given solid modelers and we've been given surface modelers. Surface modelers just model surfaces. You can't really do any property assignment to any of this. And solid modelers are just not made for the way architects design because the amount of data will be so large that you really cannot do proper justice. That's why if you were to look at Revit, I know people who consider it that, yeah, you just have to switch on Revit and go for a coffee and come back then it will load that design. I mean, you were talking about an i7 computer with 16 GB RAM and all kinds of bells and whistles, but it won't handle that. And why? Because that there are solid modeling aspects inside Revit. It can't handle the data. It's too huge. And this is the kind of geometrical principles. They're not really explaining this to all of us. That does it in a third way, which does have the capability to handle the solid, not to the extent of the really solid modelers. Like you can't see do right now, at least in this version, which I have. In future version, it can be done. That how to find out whether that thing can be crushed and things like that. That was used actually in two research projects for energy calculations of building with IIT Bombay. I conducted the research along with me. A paper was published by Dr. J.K. Nayak and me together, explaining how we went about modeling and figuring out the heat loads in that particular research. That was just a proof of concept. I need people. I need people to come and work with me. Okay, you don't have to feel bad that I've got this nice big. I've cultivated this mustache, by the way, and I am trying to look old, but it's really nice working on all this. And there's a lot of very interesting examples which can be modeled. Like you can actually talk about the whole time saver standards and Newford standards in the format of that, so you can actually understand what these buildings are and how we can do a good job in our own designing. So thank you so much. I hope this was reasonably informative, and I hope we can all really contribute something really meaningful to architecture. Thank you so much.